So I'm saying when we have losses in pipes, these losses or energy losses can be categorized under mainly two subheadings. That is the major losses and the minor losses. The major losses are basically due to friction or fluid friction in pipes, and these are calculated using the Darcy-Weisbach formula and the Chase's formula. The minor losses are basically due to sudden expansion of a pipe, sudden contraction of a pipe, a bend in the pipe, pipe fittings, and so on, an obstruction in the pipe. You could, in the process of installing that pipe, soil could enter that particular pipe. So that soil is going to act as an obstruction in the pipe. And so as water flows through that particular pipe, it is going to experience some resistance. And that resistance is actually what gives it an energy loss. Because it will mean that if you are pumping, the pump needs to do extra work. Yes, the pump needs to do extra work to ensure that the fluid goes via that obstacle. Then pipe fittings, usually, when you have fittings like unions, you have joints, you have reducers, all of those fittings result into loss in head of the floor. Then the bends and others. Then sudden contraction. For example, if you have a reducing member or a reducing fitting or a reducer, this reducer is going to be converting the pipe from a higher diameter to a smaller diameter. So meaning at that point where you're transitioning from high diameter to low diameter, then you have a loss. That is if it is sudden, like you have a sharp. So I'm talking about losses. Let me put something here. So I'm saying the losses in the pipes. So losses in the pipes, we are saying we have major losses, and we have minor losses. So under major losses, we said these are due to friction, and we said we use Darcy. Then we have Darcy-Weisbach. We have Darcy-Weisbach, and then Chase's formula. Then under minor losses, so minor losses, we have what we call loss due to one, sudden expansion. We have loss due to sudden contraction in the pipe. Then we said we also have due to fittings. We said the bends. We have obstruction, etc. Now we said for sudden expansion, you have a pipe coming smaller, then it suddenly expands. So when it suddenly expands, it is going to create what we call eddies. The swirling of this fluid are rotating around here, okay, even here, rotating and falling back. So these eddies result into what we call head loss, and this loss will be called head loss due to sudden expansion. After these losses, finally the fluid will follow its normal profile. So this is flow. This is the flow direction. Then when we talk about sudden contraction, is just the reverse of this. Sudden contraction is just the reverse of this. So you'll have a pipe coming big, then it suddenly reduces in dimensions. So again, let me redraw this. So again, this because of the eddies, because of this obstruction here, the fluid will hit here and then falls back. So somewhere, somehow, it is going to create what we call a vena contracta. And this is actually like that. So around here, you have what we call eddies. And it's these eddies that we called them. These are eddies. So you also have what we call eddies here. This is the direction of flow. So the eddies come from the swelling of the fluid, causing flow to be rotation around here, causing rotational flow, which further leads to losses. Okay, so we shall later on see how to calculate the head loss due to sudden expansion and head loss due to sudden contraction. So in the study of this, we shall be basically talking about heads because the application of Bernoulli's equation gives us the heads of the fluid. Energy is represented in terms of heads of energy. How much energy is the fluid carrying from point to point is actually experienced in terms of H, which is going to be in meters. When you want it, you can later on convert it into joules and also in watts. So let's look at the loss of energy due to friction, and we look at the Darcy-Weisbach formula. So Darcy-Weisbach formula is given by HF, which is the head loss due to friction, equivalent to 4 times F times L times V squared divided by D times 2G. So we are saying we are talking about Darcy-Weisbach. So it gives us what we call head loss due to friction, head loss due to friction, and is given by HF, which is now going to be F. This is 4 times F times L times V squared divided by D times 2G. So that means we can be able to obtain the head loss if we are given the length of the pipe. So L is the length of the pipe portion. F is what we call the friction factor. And this friction factor is a constant for a given pipe material, such as HDP GI, so HDP, HDPE, PE, PVC, and GI. But also, these are defined by given you can have other factors that could determine this friction factor, but in most cases, it depends on the plastic material or the material of the pipe itself. We can look at maybe, let me get one here. So can say friction factors. Okay, in most cases, we use what we call a Moodle graph or a Moodle chart. And this Moodle chart is used in pipe flow calculations to determine the Darcy friction factor. This is using FD. For fully developed turbulent flow, it relates the Darcy friction factor on the y-axis to the Reynolds number on the x-axis with a series of curves representing different values of relative roughness for the pipe. So to use the chart, you find the Reynolds number, then you trace a vertical line up to the curve corresponding to the relative roughness, and then you trace a horizontal line to the y-axis to find the friction factor. So we will look at what we call Reynolds number, but Reynolds number in most cases is just a constant, a dimensionless constant that is used to determine whether the flow is either turbulent or laminar. It gives us a ratio of what we call the inertial forces to viscous forces, and that's what we use to predict whether the flow is going to be laminar or turbulent. So let me check here. Let's see. So when you check on this graph or on this chart, if, for example, you want to determine the friction factor, you will first of all have to look at the Reynolds number. Yeah, so if the Reynolds number is in powers of 10 to the power 3, then it will be between this and that. So this is likely to be like, let us say maybe 3,000. Let us maybe take 5,000, something like that. So you move. So if you move, you will find that this flow is a turbulent one. And then you're supposed to look at the horizontal line. The horizontal line is actually what is giving you the coefficient of friction. Then the roughness is actually what was given by some constant divided by the diameter of the pipe. So here, the value that you pick on this other side, like now if I was to pick the friction factor for this from 5, I would move up. So the roughness, the relative roughness, if the relative roughness is in 0.6, then I would move up there and then determine the friction factor, coefficient of friction F as 0.8. If it falls, for example, here 0.05 to 0.06, if it is in between here, you just take a rough estimate or you take average of 0.07 and 0.08, add them, divide by 2, and you'll get a rough estimate of the friction factor. So let's go back. So that is exactly what we use. And then L is known, the V is the fluid flow velocity, and D is the diameter of the pipe, then G is the acceleration due to gravity. So we can go ahead and say V is flow velocity, D is the diameter of the pipe, and then G is the acceleration due to gravity. You can say G is the acceleration due to gravity. So that one is done. The Reynolds number, as we said, the Reynolds number, we need to write the Reynolds number. So we said the Reynolds number, RE, is given by, we use rho V L divided by nu, or we can also say it is V times L divided by small v, whereby rho is the density of fluid, nu is what we call the dynamic viscosity of the fluid, which determines the ability of the fluid to oppose any shearing forces against that fluid. Yeah, so this viscosity is the internal fluid friction, which determines the capability or the capacity of the fluid to resist any shearing forces. Then this small v, let me write it properly. The small v is what we call the kinematic viscosity. And this kinematic viscosity is given by dynamic viscosity out of density of the substance. Then this big velocity, big V is the velocity of the fluid. Now, if this Reynolds number is less than 2000, we call this laminar flow. And this is always done for pipe flow. So we can use these dimensions. We can use these dimensions to determine the Reynolds number. Next, if the flow has a Reynolds number above 4000, then we call this turbulent. If it is this, the flow is having Reynolds number between 2000 and 4000, okay, then it will have both. Will have both laminar and turbulent characteristics. So I've talked about that. In the future, if you meet that kind of scenario, then just remember what we have said. Yeah, so less than 2,000, then we have what we call viscous flow, but in most cases we call it laminar. If it is above 4,000, then we call it turbulent. Okay, so let's talk about Chase's formula. And Chase's formula is also simple. So let's talk about number 2, Chase's formula. So this Chase's formula is none other than HF. It also gives us head loss due to friction in pipes, and is given by HF is equal to F prime times P out of A. Let me So we are saying this HF will equal to F prime divided by rho G. We multiply it by P out of A times L times V squared. Now, we have to remember that obviously HF is head loss due to friction, and then we are saying that Chase's formula is given by HF, which is equivalent to F prime divided by rho G. We multiply it by P out of A multiplied by L times V squared. And we said HF is the friction head loss, or head loss due to friction. And next we know that rho G is the specific weight. You can call it specific weight of the fluid. Next is that P is the pressure. No, P is the weighted, not pressure. It is weighted perimeter. Is called weighted perimeter. Next is that A is actually what we call the area of cross section. Area of cross section of the pipe. So L is the length of the pipe. Now A out of P is what we call hydraulic mean depth or hydraulic radius or hydraulic radius, and in open channel flow and in all others we always denoted by M. We always denote it by M. So we need it also define. We need to define this F prime. Any question? No. So we need to define also this F prime. F prime is also a friction factor, but for it is also calculated by other quantities. I'm trying to find a way how we can calculate that constant. So finally, you will have your HF, which is going to be F prime out of rho G. We multiply it by R. Remember, we had this other component. This component is 1 out of M. Yeah, because this is P out of A, and we know that M is equal to A out of P. So this is going to be times 1 out of M, and then we multiply this by V squared. So we know if we actually made this V squared the subject of the formula, we just want to get the final expression for chase. You may not need to derive this. In any case, maybe if they ask it, but I have never seen where they ask this. They expect you to just have mastered this. So this is going to be HF times rho G out of F prime. We are multiplying this by M. And then this is going to be out of R. Yes. So we are getting some formula here. We know this rho G out of F prime is actually going to be a constant C, which we call Chase's constant, called Chase's constant. And then this component HF out of L is equal to I, and this is given by head loss per unit length. So this becomes head loss per unit length of the pipe. And finally, if we know that V squared is equal to C, okay, times M times I, then that means V is going to be square root of C times square root of M I. So this is still a constant C, and therefore we can say let's create more space here. So finally, what we call Chase's formula, Chase's formula is V equivalent to C times square root of M I, whereby M we called it hydraulic mean depth, which is equal to, we said that M is equivalent to some value, okay? And that value is what we said is weighted area over weighted perimeter. So weighted area or area of cross section over weighted perimeter. Then that I is equal to HF out of L, which is the head loss per unit length. So that means if we wanted flow, if we wanted to get flow, then we could get the cross-sectional area we multiply by this V. Okay? But this would also be possible if we know the head loss and we know the length over which we are analyzing. So all of this will help you to determine the head loss due to friction. In any case, I could be having this C, I could be having this V. I have the hydraulic mean depth, I have the L, so I can get the HF. So from here, you could just look at this example. Find the head loss due to friction in a pipe of diameter 300 millimeter and length of this, through which the pipe is flowing, through which water is flowing at a velocity of 3 meters per second. So using that formula, you would just use this. You know it is 4 times F times L times V squared divided by D times 2G. Okay? So that means in this formula, they want you to use V, which is the kinematic viscosity. So kinematic viscosity, if you are to use it, then you would reduce this. You would need to calculate what we call the Reynolds number. And after getting the Reynolds number, you can get the F. Anyway, this was given here. Yeah, so if you calculate the Reynolds number, you would see if it is less than 2000 or not. So like here, you can see it is greater. So that means you would use this formula here. Maybe I can repeat that. Okay, so sometimes you may, this F is given on a graph, like a model chart, like we saw earlier. But sometimes you may need to use the numerical values, the analytical values or analytical formula to be able to calculate that F. So let's also note that for analytical values of F, we use F equal to, we said 16 out of RE for RE or Reynolds number less than 2000. Next is that if it is above 2000, then F would be 0.079 divided by Reynolds number to power 1 out of 4. Yeah. So that means for a Reynolds number between 4,000 to 10 to power 6. So we use this. So for our problem, you can see that when you calculate the Reynolds number, V times D divided by V, this small v, or what others call nu, The stock units is what we use for kinematic viscosity, but also we use other units called meters per second. I mean square meters per second, and one stock is actually equivalent to 1 times 10 to the power negative 4. So if we have 0.01 stock and we want it in standard units, then we would multiply by 1 times 10 to the power negative 4, and we have it in meters per in square meters per second. So after getting this that we are calling the Reynolds number, yes, then we are able to determine whether it's less than 200, 2000 or above. So then we will be able to determine which formula of F to use. So you can see here, it's a very big value, so we are using this formula to get this F. So that is the F we are going to use in the Darcy formula, Darcy-Weisbach formula, and then we will be able to get 0.7828 meters. Then in the Chase's formula, we have to determine M. So M itself is hydraulic mean depth. So the hydraulic mean depth, we said that should be, okay, for a pipe, maybe let us say for a pipe, yeah, for a pipe, we could say that is D out of 2, because I don't know whether some of you have calculated. Let me go on our page and we write that. So we could maybe basically go through that, but I doubt whether anyone will ask you this number, but let's bother ourselves to calculate. Yeah, so what we are going to do is that we know that M is equal to A out of B. Okay, so for a pipe that is flowing full, the perimeter, weighted perimeter, will equal to the circumference. Okay, and that circumference will be 2 pi r, which is pi d. Then area of cross section is pi d squared out of 4. So that means this M will be pi d squared out of 4, again divided by pi d. So what does that mean? I'm going to cancel this and that. Pi and pi will go. So I'll have d out of 4. So meaning our M will equal to d out of 4. So if d itself is given by, when you check in the calculation, I mean in the answer, in the question given, you'll find that d is 300 millimeters. So that's why we have 0.3 divided by 4, and we have that value. Then HF divided by L, we already calculated our 0.7828 as HF. So we divide it by 50 and we have that value. So finally, what we would get, we are looking at Chase's formula. So Chase's formula, okay, like here we didn't have it. So we are calculating, we are looking for it actually. So let's go here. We go ahead and say this is 0.3 divided by 4. So we have 0.075 meters. So we have V, which is C, times square root of HF divided by L. times 0.075. So what we are going to do is to look for this C. We already know that this C is given by what? C is given to us as 60. So then we just have to substitute in. So C is 60. And then V is also given. V is 3 meters per second. So from here you just say V squared out of C squared is equal to HF divided by L times 0.075. Because for us to get this HF, we just have to square both sides. So when you square both sides, then this will also carry a square, and this will also carry a square. So we'll have V squared out of C squared, 3 divided by 60 squared. Then we multiply by 1 out of 0.075. We'll get HF. So we multiply. Okay, we can leave it under that. Then that means HF will be 9 out of 3600 if I square this, times 1 out of 0.075 times L. L is given us as 50. So from there you can get your value as 1.665. So you can go ahead and try out these questions. They are really so direct. Okay, they are so direct. Probably maybe what we could have missed out was the formula for this, the formula for Reynolds number. Reynolds number. So L is the characteristic length, but this is the same as pipe diameter. So if you find, let me note that. So we said that Reynolds number is equal to rho times VL. This is divided by nu. Okay, and L is the characteristic, what we call the characteristic, which can be even pipe. So if you find also Reynolds number as rho VD out of rho, then you don't ask yourself why. Obviously this will continue and be, you remember we said nu out of rho is equal to small v, and then finally, let me create more space here. Then Reynolds number will be V times D divided by the small of v, which other people call nu. So divided by nu. So that is it. Try out these numbers They are all about calculating major losses. So let's talk about the minor energy head losses, which is the main aspect that we need to discuss tonight. Maybe before that, let me see. If you're calculating the head loss, in this example, they are saying an oil of specific gravity 0.9 and viscosity 0.06 poise is flowing through a pipe of diameter 200 millimeter at the rate of 60 liters per second. Find the head loss due to friction for a 500 meter length of pipe. Yes. And find the power required to maintain this flow. Maybe we can try this before we go the other. So we are told that an oil of specific gravity 0.9 and viscosity 0.06 poise is flowing through a pipe of diameter 200 millimeter at a rate. So we have a pipe which is 200 millimeters, and this is the same as 0.2 meters. Then Q, which is the flow rate, is 60 liters per second, and this is the same as 60 divided by 1,000 cubic meters per second, which gives us 0.06 cubic meters per second. Then we are to get the viscosity and convert it. So that viscosity nu is 0.06 poise. So if it is in a poise, I remember we said that 1 poise is equal to 1 Newton second per square meter divided by 10. Yeah, so 10 times a poise will give you 1 Newton second per square meter. So that is the conversion that you can do for dynamic viscosity. So meaning that for us to get this value in Newton second per square meter, which are the standard units, then our nu will be 0.06 divided by 10, which gives us 0.006. Yeah, so this nu will be 0.006 Newton second per square meter. This is what everyone should be aware of by now. So if you cannot convert the units, then it becomes a little bit hard for us. So what next? Find the head loss to friction. So the length that we are analyzing is 500. So F is equal to 500 meters. So length of pipe that we are analyzing. Yeah, so here we can see you can use any method, but I can see that what is favorable here is the Darcy-Weisbach. So using Darcy-Weisbach formula, where HF is equal to 4 times L times V squared times F divided by 2G times D. Yes, so that means we have L, we have the V, we don't have the F. Let's look for Reynolds number. Reynolds number, first of all, is given by rho times V times D divided by nu. So this is going to be, we know the density. Yeah, we know the density because we have specific gravity. Let me put it here. So density will be specific gravity times 1,000. Everywhere you see specific gravity is 0 point something, then whenever it is given like that, multiply by 1,000, and then you have it in kilogram. You have the density in kilogram per cubic meter. So this will be 0.9 times 1,000, giving us 900 kilogram per cubic meter. So we're going to put it down here. So we are going to have Reynolds number as 900 times V. If the V is not given, then we look for it. Yeah, so here, again, we shall use what we call the continuity equation. So times, here we can multiply by V times the diameter. The diameter is given as 0.2. And then the 0.06, actually 0.006, which is nu. So our task is to get V. We know Q is equal to, so from Q is equal to VA, this is continuity because this is flow in a pipe. So those equations, the Bernoulli's equation, then continuity, all those two equations go hand in hand with each other. So in most cases, if they give you flow and it is flow rate, and we are talking about flow in a pipe, then if you don't have velocity, then you have to use the continuity equation to get it. So let's get it. So we already know that Q, okay, let's just get V. So V will be Q divided by A. So Q is already given. We have it as 0.06. We have it as 0.06. 0.06 divided by A, which is pi, times D, which is 0.2 squared divided by 4. So V, I can see we have 1.91 meters per second. So we bring it in here, we will have RE, which is the Reynolds number, and that will be 900 times 1.91 times 0.2 divided by 0.006, which is nu. So RE is giving us something 57300. So this means this value RE is greater than 2,000. So meaning F will be 0.079 divided by RE to power 1 out of 4. So we shall get 0.079. These are formulas that have to stick in our mind. So 5300 to power 0.25, because a quarter is the same as 0.25. And F, therefore, is 0.0051. Now, again, we know that HF is equal to 4 times F, which is 0.0051, times L, which is 5,500, times V, which is 1.91 squared. Then we divide it by D, which is 0.2, times 2 times 9.81. So HF finally becomes what we have as 9.48 meters. So these are just why I'm actually doing these things faster, not to, spend a lot of time here, is that they are just direct things. So given time, you just have to sit down, make a review, and these things will stick at the back of your mind. So if the question is asking the power required, we create more space here. So we are going to talk about power required. The question wanted, find the power required to maintain this flow. Power required to maintain. As you see, there is head loss due to friction. Therefore, the system must spend some power or some energy to maintain this flow. So the question is asking us the power required to maintain this flow. And how is it going to be spent? Via a pump. We are going to be supplying the energy to the pump to maintain this flow. So we know that power, first of all, is equal to energy out of time. The energy transferred in a unit time. So here, the energy that is going to be discussed is basically the potential energy, and it's this potential energy which is going to be transferred over this time as what is going to result into the power that is going to be spent. So what we can do is to say we shall have the mass out of time times gravity times h. So what is mass? Mass itself is equal to density. Density times what? Density times volume. But remember, this is mass out of time. So if we put this out of time, then volume out of time itself is flow. Good. So that means the whole of this formula, power, will be, what is here is going to be rho times Q. So rho times Q times G times H, which is now HF. So that for that matter, therefore, this will be 900 times flow, which is 0.06, times 9.81, times HF, that is here. Because this energy is to overcome the friction and also move this fluid. So since we are spending energy on friction, then we shall use the head loss due to friction here. So we shall multiply by, this is 9.48. 9.48. So if we divide it by 1,000, then we shall have it in kilowatts. So finally, this power becomes 5.02 kilowatts. Okay, so let's go to, this is what actually I wanted us to understand. In the future, if they ask you to determine the power that you're giving to the pump, it is always going to be rho G or rho Q times G times H, whereby H is going to be that head the pump is overcoming. If you divide it by 1,000, you're converting it to kilowatts. I repeat, if they ever tell you to determine the power required by the pump, then it will be the density of the fluid times the flow rate of the fluid times the head the pump is going to overcome times the acceleration due to gravity. If I divide it by 1,000, I'm converting this to kilowatts. If I leave it without dividing it by 1,000, then it will be in watts. So let's look at minor energy losses, and basically here we are going to discuss the loss of head due to sudden enlargement. So let me copy this. Now, loss of head due to sudden enlargement, we earlier on talked about it and we said that this is part of the minor losses. So as there is a change, a sudden change in pipe dimensions, we happen to create what we call eddies. So it is these eddies that result into these lead to head loss. There is a swelling of the fluid here, falling back and forth, so there is energy dissipation around these areas, and it's what actually results into head loss. Now, when we take assumptions of a control volume, we realize that when fluid is flowing from this end and is coming out from this end, the control volume is in between 1 and 2. So as it is exiting, there is a force that is going to be acting on it. So when we refer to the dynamics of a control volume, then you'll find that this force due to pressure at point P2 is going to be acting in opposition to the force due to pressure at point 1. So that's why you always find that P1A1 is, you know that force is equal to pressure times area. So that's why we have F at 1 is equal to P1A1, and force at 2 is equal to P2A2. So these forces are opposing each other, and the explanation is just from the dynamics of a control volume. All forces are always going to be acting towards the control volume. So this side, we're having flow going to this side, but because forces are going to be acting towards the control volume, then this P2A2 is going to act in opposition to P1A1. So for that matter, therefore, P1 is the pressure at the section 11, V1 the velocity of flow at that section, A1 at section 11, and P2, V2, and A2 are the corresponding values at section 22. In any case, if they ask you to derive this expression that we are going through, this is where exactly you begin from. You draw this diagram, you define these pressures, areas, and the velocities, then we continue. So we say that due to sudden change of diameter of the pipe from D1 to D2, the fluid flowing from smaller pipe is not able to follow the abrupt change. We have already explained that. So there is going to be some turbulent eddies that are going to be formed there. And so for this matter, you'll find that the pressure in between here, between P1 and the pressure between 1 and 2, there is a point where the eddies are formed. This pressure here is not going to be the same, okay? So it is going to be called P prime. So the pressure at the eddies are occupying an area A2 minus A1. Yeah, because we know the bigger diameter is A2, the smaller diameter is A1. So that pressure, that area that is occupied by the eddies is going to be A2 minus A1. And the pressure acting there is called P prime. Now the H is the head loss due to sudden enlargement. From Bernoulli's principle, we know that for a real fluid flow, P1 divided by rho g plus V1 squared out of 2g plus Z1 is going to equal to, the losses are always added on or on the right hand side of the expression. So we will have P2 divided by rho g plus V2 squared divided by 2g plus Z2 plus loss due to sudden enlargement. Now, since the pipe is horizontal, so this is an assumption that the pipe is horizontal. Pipe is horizontal. Okay, so that we eliminated the Z1 and Z2. Therefore, P1 divided by rho g minus P2 out of rho g. Let me just even combine that. Let me just combine that. So I'll have P1 minus P2 out of rho g. This is equal to V2 squared minus V1 squared out of 2g plus HE. So I call that equation 1 because Z1 and Z2 have cancelled out. That's what happens. So we need HE, so we can still say, let me take it further this other side. Let's take it further and say this HE is P1 minus P2 out of rho g. Okay, then we are going to add, when this negative V1 squared crosses equal signs, it becomes positive V1 squared. So minus V2, because this was positive, it becomes negative, divided by 2g. Now we are here. We can call this equation, we can call it equation I. Now what next do we need to look at? We also need to look at the force. So we shall consider the control volume between 1, 1 and 2, 2. So between 1, 1 and 2, 2, the force, the resultant and horizontal force acting on it, I mean the control volume, Fx, let's call it Fx. This Fx will be due to P1A1, the resultant force, so we shall have P1A1. We add another force, P prime into A2 minus A1. Yeah, because we say the A2 is greater than A1. And the pressure that is there is P prime due to eddies. Then we are going to subtract P2 A2 because we can see according to the dynamics of the control volume, this force is acting in opposition to P1 and A1, P1 A1. So we shall just open brackets here. But before that, experiments show that P prime is approximately equal to P1. So it's a good approximation, P1. So what we do, we shall say that this Fx will equal to P1 A1 plus, now this becomes P1. Okay, we open, or we can maybe leave it there, then we say minus P2 A2. We can open brackets here now. So Fx will be P1 A1 plus P1 A2 minus P1 A1 minus P2 A2. Someone very critical can see that now we have some things to cancel. So this and that will go away. So Fx will equal to P1 minus P2 into A2. So we can call this equation 2. Yes. So we continue and say that also consider the momentum of the fluid per second. So momentum of the fluid per second in that direction. So in the direction of flow. So we can say that at section 1, 1, momentum is going to be what? Momentum per second is going to equal to, we know that momentum is mass times velocity. Okay, so but now if we talk of momentum per second, then that means we are dividing this by time. Yes, so but what is mass? We know mass out of time is equal to rho times volume. So now divided by time, this becomes what we call rho times Q. Yes, because the volume out of time is flow rate. But Q itself is equal to area times velocity. So that means at section 1, 1, the momentum per second will therefore equal to, now we substitute in here all these quantities. We shall have density times area A1 times V1, then times V1, because remember we said it is multiplied by velocity this side. And the whole of this rho A1 V1 is only this mass out of time. So therefore, the momentum per second will be rho times A1 then V1 squared. Likewise, at section 2, momentum per second will be density rho, since it is the same fluid, it will have a constant density, times A2 V2 squared. And the change in momentum don't worry, I will share this summary so that you go through it. The change in momentum per second will equal to rho A2 V2 squared minus rho A1 V1 squared. So we can again create more space here. So from here, we know rate of change of momentum is equal to force, and this is second Newton's law of motion. So that means the force Fx is also equal to rho into A2 V2 squared minus A1 V1 squared. So what does that mean? I'll just look at the equation what? Equation 2. Therefore, from equation 2, we have the fact that P1 minus P2 times A2 will equal to density into A2 minus V2 squared, times V2 squared, then minus A1 V1 squared. So that will tell you that I can get P1 minus P2, I divide by rho, okay? And this is equal to A2 also into V2 squared minus, so this one we can't factorize out the A2. So we can still say that this is A2 V2 squared minus A1 V1 squared divided by A2. But again, from continuity, from continuity equation, we know that A1, V1 is equal to A2, V2. So meaning we can eliminate A1 here. So meaning A1 will equal to A2, V2 divided by V1. So if this was maybe star and this was 3, so I can put 3 in star. Yes. So if I bring it in here, that means I'll have P1 minus P2 out of row. This will equal to A2 V2 squared minus A2. This is going to be V2, okay, that I'm substituting in here, then times V1 squared divided by V1. So meaning some things are going to cancel, so this and that is going to go away. And what does that mean? Still, this is out of A2, okay. So meaning this A2, this and that are going away. So what does that tell us? It tells us that we will have P1 minus P2 out of row, which will equal to V2 squared minus V2 V1. V2 squared minus V1 V2. Very good. So can I divide both sides? So divide both sides by G. So what does that become? P1 minus P2 divided by rho G will equal to V2 squared minus V1 V2 out of rho G. I haven't changed anything here. I'm just doing some manipulation so that I get something that is similar to this according to equation 1. Equation 1 is up here. So that I just bring whatever I have, I substitute in here and I get HE. Because all the struggles that we are going through, we want HE. So therefore, from equation 1, HE equivalent to P1 minus P2 out of rho G. So I substitute it with this. So V2 squared minus V1 V2 divided by G plus up there we had is it V1 minus V2 or V2 minus V1? So let's check. It's V1 minus V2 squared. So let's write that V1 squared minus V2 squared out of 2G. So HE will equal to, we look for LCM. So LCM here is 2G. So divided by this, I'll have 2V2 squared minus 2V1 V2. Then when I bring it here, 2G divided by this, it will be 1. So plus V1 squared minus V2 squared. So correcting right terms together gives me V2 squared plus V1 squared minus 2V1 V2 divided by 2G. And if I look at this component, the algebra tells me if I have A plus B squared, now let me make it like this. Squared, this is going to be A squared plus B squared minus 2 B. So if I relate it with what I have here, then HE will give me V1 minus V2, everything squared out of 2G. Therefore, the head loss due to sudden expansion, head loss due to sudden expansion, HE is calculated using V1 minus V2, everything squared divided by 2G. So if this problem is given to you to prove that the head loss due to sudden expansion in a pipe is V1 minus V2, everything squared divided by 2G, then you start from here, you move, you consider all those concepts, then you conclude from here. Now I want to rush very fast to the expression for sudden contraction, so that maybe some people can ask questions. That is the expression. Now let's look at this. So this is loss of head due to sudden contraction. Again, as we earlier on discussed, you said sudden contraction means you have a pipe that is of a particular dimensions, and then at a particular point it changes. And here it is changing from high dimensions to lower dimensions, and there is a sudden change. So again, you also have such kind of arrangement, and you'll have the eddies around this point. And these are the eddies that are going to lead to loss of head. Now, in analyzing this problem, we also consider a control volume. And the control volume is going to be basically between 1, 1, and 2, 2. And in the middle there, we have what we call the vena contracta. So this is what we call vena contracta. So that is the vena contracta. This kind of arrangement is what we are calling the vena contracta. And it is these eddies here that are going to result into head loss. Now, when you analyze this, you realize that between CC and 2, 2, there is again some kind of sudden expansion. So there is some sudden expansion, and this is what actually causes loss, head loss. So the head loss due to sudden contraction is actually complemented by head loss due to sudden expansion at the vena contracta. So if we take area at the vena contracta to be AC, VC to be the velocity of the fluid there, then A2 to be the area at section 2, V2 at section 2, and HC to be the head loss due to sudden contraction. Then we shall find that HC is going to be VC minus V2 squared divided by 2G. So this is simpler than the head loss due to sudden expansion. So here we start from the vena contracta. So we utilize that head loss expression due to sudden expansion to derive the expression for head loss due to sudden contraction. So here we will find that we do a lot of some little bit of manipulation here, and we say that this is VC divided by V2 minus V2 divided by V2, okay? And we square this. Sorry, let's create more space. So we are saying HC is equal to VC minus V2. This is out of V2, this is out of V2, this is 2G. So we can also say we can multiply by V2 here, and we square here. So when you square this, we have not changed anything. Let me see, we will have not changed anything here. Because at the end of the day, when we open here, it becomes VC times V2 divided by V2. So those two will cancel, and this V2 will also cancel here. Now, this is what is going to happen when we expand. This is going to be V2 squared out of 2G. Then we remain with VC out of V2 minus 1. So it is also squared. I think we can see that. So meaning we need to say using continuity equation A2 V2 is equal to AC VC. When we apply continuity equation between CC and 2, this is what we have. So that means basically we are going to have a VC out of V2. Let's get it here. If we have AC out of A2, what is that going to be? This is going to be V2 out of VC. Yes, so, but AC out of A2 is called CC, and CC is called coefficient of contraction. So it is a constant. It is a constant. Therefore, if we bring it in here, this means we will have CC equivalent to V2 divided by VC. That means if we do a little bit of manipulation here, it means 1 out of CC will equal to VC divided by V2. So therefore, from this equation, we can say from star HC will be V2 squared out of 2G into 1 out of CC minus 1 squared. So whereby we can let 1 out of CC minus 1 squared to equal to K. And therefore HC becomes V2 squared out of 2G times K. So given K, we can determine HC. Okay, so that's where we are. Now, if we have any problem, let's go back to this other area. You can see if we have our coefficient of contraction to be like 0.62, yeah, then K will be 0.375. Okay, so if the value of C is not given, the head loss due to contraction is always taken as, so if CC is not given, then HC can be calculated from HC is equal to 0.5 V squared out of 2G. So that is if it is a velocity at 0.2. So given this question, find the head loss in a pipe of diameter 200. So let me capture this. So let's do this number. Okay, so we are saying the head loss Find the head loss of a pipe. Diameter 2. So diameter is 200 millimeter, which is 0.2 meters. This is D1. Then D2 is 0.4 meters. Q is 250 out of 1,000 cubic meters per second, making 0.25 cubic meters per second. So that means we are able to get Q, which is equal to AV, okay, meaning we can as well say AC VC is equal to A2 V2 is equal to A1 V1. Yeah, so we are able to determine the coefficient of contraction. We are able to determine the V2, and therefore we are able to compute that HC. So, this question is looking at sudden enlargement. So, sorry, let's do sudden enlargement. So, that means the question is just very direct. So, we shall say this is 0.2 meters, 0.4 meters. So, what is HE? This is V1 minus V2, everything squared out of 2G. So we know that V1 is equal to Q divided by A1, and this is 0.25 divided by pi times 0.2 squared out of 4. You get that, then V2 will be Q out of A2 also, and this is 0.25 divided by pi times 0.4 times 0.4 squared out of 4. So HE will therefore become what? This is supposed to be 7.96 minus 1.99, everything squared, divided by 2 times 9.81. So HE, when you compute it very well, should give you a 1.816 meters. And that's all. So these questions come when they are really very simple. Okay, so the next one could be contraction. Let's see if we have one for sudden contraction. Yeah, also here, if they require a power lost due to sudden, so it could have a question power lost due to sudden enlargement. then that power will equal to rho Q, we say dG times HE. Divided by 1000, this will be in kilowatts. So here you have the 1.816 times 9.81 times the flow, which is 0.25 times 1000, which will be the one for water divided by 1000. So finally you get your answer. So that power should give you an answer in kilowatts. For sudden enlargement, sudden contraction, they can give you, let me see this question. Let me check here. I'm seeing some question here. Yeah, you can try out this. A horizontal pipe of diameter 500 millimeter is suddenly contracted to a diameter of this. The pressure intensities in the large and small pipe is this and that. Find the loss of head due to contraction of this. Also determine the rate of flow of water. So here you would now apply the Bernoulli's equation, you apply the continuity. It's as if you're doing it from first principles. You've been given CC, so later on it's just a matter of substitution, and you'll be able to get that answer. So you should be able to get 0.751, and the flow rate should be 268.3 liters per second, or 0.2683 cubic meters per second. So members, I want to stop here and just invite any questions.